Okay, look, in the last part we were really addressing the switch issue. This is the crossing switch. And remember, we were talking about a situation, of course, where somebody might momentarily press this switch. We wanted to capture that. We wanted to latch that in, okay? And so we looked at using an SR latch for that purpose, all right? So we'll just recap that very briefly. So here we have the SR latch. Here we have what could be the crossing switch here. This could be a push button switch. In this case, this was a normally open switch. All right, I asked you to go away and really think about this situation. Let's supposing, as I said to you, reset will be generated from the state machine. Let's look at the initial situation though, where perhaps reset has not been generated from the state machine. You are in your 0, 0 state. So let's say this reset at the moment is sitting here at a 0. Okay, so reset is sitting at a 0. What is the other side of this inverter here? It is a 1, isn't it? Okay. Yep. Okay, supposing somebody presses this switch. All right, so that switch closes. All right, there it is. What's this logic level here? Direct connection to ground. This logic level would be what? A 0. All right, 0. We invert the 0, so we've got a 1 sitting here. So we've got a 1 sitting here and a 1 sitting here to the right of each of those bubbles. So we've got a 1, 1 input at this AND gate here, which gives me what over here? Gives me a 1 sitting over here. And so I've got a 0 on the reset line. I've got a 1 here. What's going to happen to Q? Q is going to go to a 1. Okay? All right. Now let's say you take your finger off the button. This switch opens up again. What happens to this logic level sitting here? This logic level goes to a 1. Okay, feeding in. Let's look at this. The other side of this inverter here is what? Now a 0. A 0 into an AND gate causes this to do what? Go back to a 0. So now we have a situation that S is a 0, R is a 0, but this 1 gets latched in. Okay? The 1 gets latched in. This won't go away until the state machine over here generates a reset signal. So instead of having the 0 here, when we move to another state, the state machine will generate a 1. And this 1 will do what? This 1 comes into here, causes reset, or R to be a 1. And then look at what's going on here. You've got the 1 coming in here. We invert this, a 0 here. So a 0 into this gate is going to force this S, maintain this S at being a 0, regardless of what somebody over here is actually doing. Okay? So when the reset is generated by the state machine, it overrides what anybody's doing with the switch, with the crossing switch. Okay? So the question is, how do we really reflect that into our state diagram? Okay, so here's our first state, north, south, green, and wait. All right, switch. Now, remember, SW now is what? It's the output, okay, it's the output, the Q output of the SR latch. That's why we now have called it SW. It's the Q output of the SR latch, okay? So in other words, if I drew the SR latch sitting over here, there's S, there's R. The Q output is what we're calling SW. That's what's feeding into my state machine. Okay, so somebody presses the switch, okay, which will force SW to be latched at a 1, and then when we get the next clock edge, the next system clock edge, we will move to this state over here where we are changing the lights, north, south, yellow, and wait. All right. Now we do need our state machine though to generate the reset, to actually generate this reset. Okay, because if we don't generate the reset, then SW will remain permanently set to a 1. So where could you generate a reset signal? Well, you could really generate it in any one of these 3 states here. You certainly couldn't generate it in the state here, because obviously that's a state that we're looking at coming out of depending upon the condition of the switch. So we could generate a reset here or here or here. So what would we do? Reset then is an output coming out of our state machine, which then would be effectively an input going into the SR latch in the arrangement that I showed you really on the previous slide. So I have to generate this additional output Here I'm just showing that being generated in this given state here. Okay? So we've fixed the switch, the crossing switch problem. But look, let's look at this, right? Now remember, we change states, what? On every leading edge of the clock. Now you might want to set your clock period, your system clock period, to what? What would be reasonable? How long would it be reasonable to have the north-south light yellow and the white light on? What would be reasonable? You know, maybe a couple of seconds, maybe 3 seconds, I don't know, 1, 2, 3, perhaps that's reasonable. Then we'll move into this condition, north-south red and wait, staying there of course for 3 seconds, and then we move into this state, north-south red, we're letting the people go. And then after 3 seconds, 1 clock period, we move back to this state here, north-south green and wait. Well, look at this. We're only staying in this state how long? 1 clock period. 3 seconds if we'd set the clock period to 3 seconds. So what does that mean? It means you are allowing 3 seconds for the people to cross the road. That's not a realistic situation, okay? So how do we fix that problem? Well, we could add more states just like this one here. So instead of going back, we go into another state like this one, north, south, red, and go. So we could add more states, okay, and maintain this north, south, red, go condition. So one thing you could do is you could have more states that would be like this one. Or alternatively, perhaps I could use maybe a counter to provide some kind of, if you like, timeout feature. Okay, now the counter, in a sense, is separate to the state machine. The state machine's looking at the counter. It may be controlling the counter, but it's a separate device to the state machine. Okay, so we could keep the state machine relatively simple, not add really any more states, and use this external device that the state machine will actually control. So we need to look now at how we could add a counter into this and how it would affect what we're doing here in terms of how long we might stay in a state such as this, north, south, red, and go. Now once again, just to emphasize, when I put outputs in these rectangular blocks, I have to specify whether they're high acting or low acting. Right now, I'm assuming each of these outputs are all high acting outputs. Okay? So let's have a look at a simple counter. Okay? Now, a simple counter, is a clocked device. In other words, it changes its state or its Q values every time you get a clock edge. Now, you can get leading edge triggered counters and falling edge triggered counters. We're going to assume leading edge triggered counters. Okay, so these Q values then change every time you get, if you like, a leading edge of the clock. Now, we're going to use the same clock for the counter as we use for the state variable flip-flops. Okay, and we'll call that, if you like, the system clock to our machine. All right, now I'm just showing you here a very simple counter. It's a 4-bit counter. It's got 4 outputs. It's got what we call a carry out. It's got an enable, and it's got a clock input. Okay. Now, there are various kinds of counters. Now, it's going to be very important for you, okay, to pick a counter and look at the data sheet to understand the pinout of the counter, to understand the functioning of that counter, how you control the enables, whether the enables are high acting or low acting, or any other features that that particular counter has. So using data sheets really throughout is a very important thing, and you need to get used to doing that. Okay? Now let's look at a count sequence, how this guy is counting, if you like, with respect to the leading edge of the clock. So we could imagine it starts off with 0, 0, 0, 0. Okay, when you get the next leading edge of the clock, it goes to 0, 0, 0, 1. When you get the next clock edge, it goes to 0, 0, 1, 0, and so on. Okay. So if you like here, what I'm doing is I'm showing you the Q values of that counter, and I'm showing you those Q values, if you like, at a time t. Then I'm showing you the Q values of the counter, and I'm showing you a time t plus delta t. Now, we've done this before. What am I really referring to there? Well, remember, this counter changes its state when you get this leading edge of the clock. And so what I'm saying is that T basically is the time just before the edge, and T plus delta T, that's T plus delta T if you like, is the time just after that edge. Okay, so the time, the condition of the counter before the edge, the condition of the counter after the edge. Okay, it's an edge triggered device. Look, a counter is really a very simple state machine in and of itself. Okay, so let's look at this. If the counter is sitting with 0, 0, 0, 0 for its Q outputs, when you get the leading edge of the clock, it's going to go to 0, 0, 0, 1. So what you would expect, it increments. If you have 0, 0, 0, 1 for this counter before the clock edge, when you get the leading edge of the clock, it goes to 0, 0, 1, 0. Okay, it increments. Now, if we're looking at a binary counter, which we'll look at in this particular case, it's going to count from 0, 0, 0 all the way up to what? 1, 1, 1, 1. Okay, and then it's going to roll back to the 0, 0, 0, 0 condition. So look, let's imagine that we've done some of that counting, and let's imagine now our counter has reached a value of 1, 1, 1, 0. Now that's the value before the clock edge. Here, before you get the clock. Clock comes along, there's the leading edge of the clock. What's going to happen to this? It's going to increment and become 1, 1, 1, 1. Okay, so that's the 1, 1, 1, 1 condition sitting in the counter. Now the carry out only becomes a 1 when the counter has 1, 1, 1, 1 for its Q outputs. So this is when that carry out becomes a 1. Otherwise, the carry out would in fact be a 0. So this is when you get the 1 for the carry out. When this guy basically rolls over to 0, so look, let's supposing now the counter was sitting at 1, 1, 1, 1 before the clock edge. When the clock edge comes, what's it going to increment to? It rolls over to 0, 0, 0, 0, and of course the carry goes away. Okay, so it's important to understand how this counter is basically counting. It is incrementing with every leading edge of the clock, and the carry out only occurs when the Q's or the Q values are 1, 1, 1, 1. It's very important to note that condition when this carry out is in fact generated. Okay, here's a slightly more complex counter, very similar. Here we have our Q outputs, Q3, Q2, Q1, Q0, okay? Here's our clock input. But in this counter, we have some inputs to it. D3, D2, D1, D0. This counter is a loadable counter. So you can have a situation whatever is placed on the D inputs could be loaded into the Q outputs. It could be loaded into the Q outputs. So look, I'm showing you two additional signals here. I'm showing you a load signal. Okay, and I'll say to you that this is a low-acting load signal, abbreviated to LLD. We have a clear signal, okay, abbreviated to LCLR. Now, I'm saying to you in this particular case, these are low-acting load and clear signals, all right? Now, for a particular counter that you're going to use in a practical situation, what do you need to do? You need to look at the data sheets. Okay, and it is the data sheets that are going to tell you, okay, what is going on as far as controlling the inputs are concerned. So it's important that you're able to use these data sheets for that purpose. So now let's have a look at if you like, a little timing diagram to look at how the load is working, how the clear is working, and how this counter is incrementing. Okay. Look, what I'm showing you here is a very simple timing diagram. Look, each one of these lines here will represent a clock edge. So if I were to draw my system clock here, what's it looking like? It's sort of looking really like this. This would be my system clock. So if I wanted to draw that, that's really what it's sort of looking like there. So each one of these lines represents a leading edge of the clock. All right. Now I'm saying that these two signals here are basically low-acting signals. Low-acting signals. So look, what I'm going to do is I'm going to maintain this guy high. Going to maintain this guy high. It's inactive at this point, isn't it? If it's a low-acting signal, action occurs when it goes low, not when it is high. The outputs of the counter, these are the Q outputs. Now I'm just showing you this in the decimal form here. It's just easier to sort of draw it this way. or write it this way. So I'm saying that the Q values now are what? 2. So that would correspond to what? 1, 1. I'm sorry, back step. That would correspond to 0, 0, 1, 0 in the case of 2. Okay, and then in the case of 3, it would be 0, 0, 1, 1, and so on. Okay, so those basically are the Q outputs. As far as the D inputs are concerned, I've got 7 sitting there, and I'm just going to hold 7 on the D inputs. That's all. Just hold 7 on the D inputs. So here we are. Let's have a look at what's going on. Okay, first clock edge comes along. This is sitting at 2 for the Q outputs. We increment, goes to 3. All right, let's hold the load high. Let's hold the clear high. So when you get the clock edge, this next clock edge, we're not clearing, we're not loading, and so the counter simply increments to 4. Okay, so we've now got 4 sitting in there. Well, let's continue to hold the load high. So there is load high, but let's now pull down, okay, the clear. So we're going to perform a clearing operation. So here it is, clear is pulled low like so. Now, these loads and clears are what are referred to as synchronous loads and synchronous clears. Okay, there are such things as asynchronous loading and clearing, where basically the state of the counter, as soon as you pull the clear, will go to 0. It won't wait for the clock edge. If they are synchronous loads and clears, this output doesn't change until you get the next clock edge, which is sitting right here. So yes, clear is active, but the counter doesn't change its value until you get the next clock edge. At this next clock edge, what is clear? Clear is 0, and so the value of the counter then becomes 0. The Q outputs then become 0 because the clear was a 0 by the time you got that leading edge of the clock. Okay, now let's imagine that the clear goes back to a 1 during this period of time like so, and we'll just hold that at a 1, and we'll hold load at a 1 like so. Well, next leading edge of the clock, which is right here, what are we seeing? We're seeing the clear is a 1, the load is a 1, so are we clearing? Are we loading? No. So the counter just increments and becomes 1. It just gets a 1 effectively, doesn't it? Okay, now let's imagine that in this period of time, we pull the load signal down to a 0 like so. Now once again, the output of the counter can't change. It has to wait for what? The leading edge of the clock. At this next leading edge of the clock, what is load? Load is a 0, and so whatever is on the D inputs here gets basically loaded then into the Q outputs on the next clock edge, and so the counter then gets loaded with a 7 on that next clock edge. Okay, now really it's very important that you understand how the clearing function happens and how the loading function of this particular counter actually works. Now the load, or rather the load and the clear signals, where are they going to be coming from? They're really going to be coming from our state machine. They're going to be outputs really from our state machine. Okay, so what I'd like you to do now is, could you really, this is the end of part 4, could you maybe take a few moments here and see how you could use one of these counters now, perhaps in your state machine, to provide a timeout function. Now maybe what your state machine needs to look at is that carry out. And remember, the carry out only occurs when the counter basically has what? In the case of this 4-bit counter, the outputs have to be 1, 1, 1, 1, or decimal 15, if you like. That's the only time you get the carry out. So could you imagine how you might use that as a timeout function? We'll take a break.